All right, let's look at example number 2. It says Bill pushes a piano across a frictionless surface with a force of 200 newtons. So we just label it F. Force of Bill is 200 to the right. His very unhelpful friend Ted pushes to the left with a force of 50 newtons. And it just says F sub T equals 50 newtons. If the piano has a mass of 500 kilograms, calculate the net acceleration. So if you ever see a problem like this, you realize it's a forces problem. And whenever you have a forces problem, you always use the 5 steps for success. All right, so go ahead, hit pause, try to work the 5 steps, and then when you think you've gotten the 5 steps, come on back and you'll watch me work it. All right, so step number 1 says draw an FBD. So I'm just going to put my FBD right on top of my picture, and I'm going to label my force of weight going down, and then I'm going to have my normal force going up. And then just to change up colors, I'm going to say my force for Bill is going to the right, 200 newtons. And this is the force of Bill, is 200 newtons. And then force of Ted is going to the left. And I'm just going to make that vector 1/4 the length of Bill's vector because he's pushing with 50 the opposite way because he's unhelpful. All right, so that's step number 1, draw an FBD. And then if we go back to step number 2, it says pick a coordinate system. And in this case, we're just going to go with our standard coordinates, where y is going up and x is going to the right. It's positive. All right, so I'm going to make a little check mark here, and I should have done this to start. I'm going to say step number 1, check. Step number 2, for success, check. Step number 3 says look at any of these vectors, and if they're not lined up with x or y, then we have to do SOHCAHTOA. So let's take a peek. My force of Ted and force of Bill are going left and right, which means it's lined up with the x-axis, so they're good. No SOHCAHTOA. If we look at the vertical direction, the normal and the weight force, they're going with the y. So that means we have no SOHCAHTOA there. So step 3 is good. I don't have to do anything. Step 4, and I'm actually going to roll up to this one so you can see what it says. Step 4 says to sum your forces in the x and y directions. So you're going to use the Greek letter sigma and the Greek letter sigma over here, and you're going to sum up your forces in the x and y. So I'm just going to come over here. Step 4, summing my forces or adding forces in the x. And for this one, I have the force of Bill going to the right minus the force of Ted. Because you can see Ted is over here and he's going to the left. And then I set that equal to m times a times my acceleration in x direction. All right, so let's sum our forces in the y direction. Sum our forces in the y. And for the y direction, I have my normal force going up and my weight going down. And that's equal to m a y. Which in this case, I know that this is a box that's sliding side to side, so it actually has 0 acceleration in the y. So I can set that equal to 0. And what that means is that my normal force is equal to my weight. Okay, there's step 4. We'll do step 5, which step 5 says to solve for what you're looking for using kinematics equations and step 4 equations. So I'm just going to go back here and I'm going to say, given in this problem, I think they give us the force of Bill here is, double check, 200 newtons. Force of Ted is 50 newtons. And then we always have our buddy gravity, just in case we need it. And I think they gave us the mass of the block too. Yep, 500 kilograms. Whoa, that's heavy. That's like over 1,000 pounds. So we'll say mass is 500 kilograms. And then the want, in this case, it says the piano has a mass of this. Calculate the net acceleration. So we want the acceleration of this block. So as they're pushing it, we want to get acceleration. And then we're going to say, okay, if you look back at all of our old equations, do we have any equation that specifically applies to two people pushing a box like this from kinematics? And the answer is no, we don't. So we don't have an old kinematics equation to use, but we do have, if you look at step 4 here, we do have an equation that we came up with. That the acceleration is right there in this equation. So we're actually going to use the equation we came up with, and the only thing we have to do is we just have to say, okay, ax is equal to force of Bill minus the force of Ted. And then I'm just going to bring the m to the other side. So basically the reason we do the step 4 is because it gives us our equations. So acceleration in the x direction is just whatever the force of Bill is minus the force of Ted because he's unhelpful, he's going against us. So we're going to say that's going to be 200 newtons minus 50 newtons all over the mass, which is 500 kilograms. So if you say 200 minus 50 divided by 500, and if I crunch that, I'll get that it's 0.30 meters per second squared. So there's our acceleration. Not a really high acceleration, but it's a really, really heavy box. And I'm just going to write my final answer, and I apologize for squeezing it in here. I'm going to put an arrow or vector symbol above the A, and my final answer will be 0.30 meters per second squared. And since it's positive, and we define positive as in the x direction here, I'm going to the right, we do have to put a direction on it. So you could say this is acceleration to the right. I'm going to say it's in the x direction, or for short, I'm going to say it's x hat. So our final answer would look something like that right there. All right, let's try example number 3. So it says, same as number 2, so that's the one we just did, but now the piano is sliding across the surface where we have a Greek letter is what we have, mu sub k. Calculate the net acceleration. So for this one, this is the physics way of saying there's friction in this problem. So go ahead and do your 5 steps for success, just like we did before. Same problem, but now the only slight variation is that we have friction. And then when you're ready, come back and we'll walk it through. All right, so first step for success, draw an FBD. So it's going to be almost nearly identical FBD to up top. So I'm just going to say, okay, normal force going up, weight going down, and then we got the force of Bill to the right. That's 200 newtons. And then we have the force of Ted, unhelpful friend. And then the thing we have to add on is friction is fighting against us in this case. So we have to go back and think, well, friction always opposes the motion. Well, in our previous question, we figured out that the box was accelerating to the right. So the box was going to the right, which means that friction in this case is going to be going to the left. So what I'm going to do is I'm just going to go ahead and actually let's stick with that green color. I'm just going to say friction is another force that we're going to have. And I'm just going to put it at the tip of that arrow, that vector. I'm just going to put the force of friction, F sub k, is going back that way. And sometimes you could put the vector right below the force of Ted vector. It doesn't really matter so much as long as it's the right length and the right direction. All right, so that's step number 1. Step number 2 is going to be the same as before. So I'm just going to make a little checklist again. Step 1 we did. Step 2, our coordinate system is going to be the same. We're still going to go x and y coordinates normal. So we'll say positive x to the right, and then we got positive y up. Step 3 says use SOHCAHTOA for any vectors that are not aligned with our x or y, but we don't have that case. We don't have any vectors that aren't aligned with x or y. So we're going to go right to step 4, which is sum our forces in the x and y. So we'll say sum our forces in the x. So we're going to have the force of Bill to the right minus the force of Ted, who's fighting against us, minus the force of kinetic friction. And it's kinetic because they told us here it's mu sub k. And remember, if that's mu sub k, that means we're going to have a sliding frictional force. And just like last time, we said equal to max. To be even Steven here, we're going to sum our forces in the y, which is going to be the normal minus your weight, which this box is not accelerating in the y, so that means the acceleration is 0. So that's 0. So that just means n is equal to w. And then just to kind of review that w is equal to mg. Just to kind of refresh that in our memories a little bit. All right, so we did step 4. So let's go ahead and say check step 4. And now after we do all of this, then we get to figure out, we're actually kind of solving for you. We do the physics format. So let's say given, want, equation. equation and the numbers. So again, the givens are going to be the same with one little variation. We got 200 newtons for Bill. We have the force for Ted is 50 newtons. I'm just going to highlight this in pink. They also gave us a mu sub k, or coefficient of kinetic friction, of not very much, 0.02. It's really close to 0, so just a little friction. And then, as always, we got our buddy gravity, which is 9.81 meters per second squared. And what is it we want in this one? We want A. We want the acceleration of this box this time, but now there's friction. So we think back, all of our kinematics equations before didn't have a specific equation for a situation like this. So we're going to look to our step 4 equations, and I'm just going to see this equation we got from step 4, N equals W equals mg. That doesn't have an A in it, so we can't use that to get our acceleration. But we can go up here, and we notice again we have an equation that has an A. So I'm going to say we can use that equation to get our acceleration of our box with friction. So let's solve this out. A sub x is equal to the force of Bill minus the force of Ted minus the force of kinetic friction all over m. And I'm going to do one extra step here because we don't have Fk. And some people are going to say, yeah, we have Fk, Mr. Laurent. It's right here. It's this 0.02. But this is mu sub k is 0.02. So we got to remember back, that's just the coefficient. And this is saying F sub k. So we're just going to make a little note here. The force of Bill minus the force of Ted minus, I'm going to kind of go off to the side. I'm going to say Fk, back in the day we wrote an equation down, was equal to mu k times n. And then we know in this case that n is equal to W, which is equal to mg. So I'm just going to say, oh, that means Fk is equal to mu k times mg. So we know that the force of kinetic friction is equal to our mu k value times m times g. So I'm actually just going to sub that in here. Mu k times m times g all over m. So for our equation that we're going to write down, we're going to say A sub x is equal to force of Bill minus the force of Ted minus the coefficient of kinetic friction times m times g all over m. And then we plug numbers, so we're at 200 newtons minus 50 newtons minus mu k is 0.02, and no units on that one, times our mass of the piano is 500 kilograms times gravity, which is 9.81 meters per second squared, all over 500 kilograms. And when you crunch that, I'm going to go to bright pink here, our acceleration turns out to be, I got 0.104 meters per second squared, and then it's positive, it's in the x direction, so I'll say x hat. And one thing to notice, our acceleration down here, does it make sense that it's less than the acceleration that we got up here? And the answer is yes. We should have less acceleration because now we have friction fighting us. So those are 2 problems using the 5 steps for success. The one note that I'll make on here, because I always have a student that asks me this, they're like, Mr. Laurent, when you're doing these problems, you used to always tell me that gravity is negative, and you'd put a negative sign out in front of gravity, and now look at, I'm just going to highlight right here. So why all of a sudden are we saying gravity is positive when the whole time throughout this year you said gravity is negative? And the reason why is this. We know that gravity acts down, but gravity is not a force. So gravity as a force, the force of gravity is what we call our weight. So I'm just going to highlight here, we already took into account that gravity was going down when we did our weight vector going down. So if we look, we put our weight vector going down, and then when we came over here and we did this, do you see how we put a negative W right there? So when we put that negative there, this negative right here, that's when we took into account that the force of gravity acts down. So now when we actually crunch the numbers, we don't want to also put the negative in here because then it's kind of like you're double counting the negative. I hope you're not freaking out thinking Mr. N thinks gravity's going the opposite way. It's just that we took it into account when we did our FBD. So thanks for watching, and go Physics All-Stars.